All right, so what we're going to go over today is what happens when two waves try to be in the same place at the same time. That's what the principle of linear superposition says. Okay, the principle of linear superposition is what happens when two waves are in the same space at the same time. Okay, yet again, more evidence that waves are not matter, waves are energy. Is it possible for matter to occupy the same space at the same time? No, it is not. Okay, but it is possible for waves. What happens though is waves have to travel through matter, through their medium. And so the medium essentially has to take a shape that will reflect how much energy the waves have at the same time. All right, so what that means is, effectively, if two waves are coming at each other and they're both up, like they're both a crest, okay, what's the shape of the medium going to look like? If we have to conserve the energy, so I've got two up waves coming at each other, will the medium get higher or lower? Higher, yeah, okay. Simply what's going to happen, guys, very simply, is you add the energies, or amplitudes in this case, of the two waves together, and you'll have the shape of the medium that results from the interference of those two waves. All right? Now, most of the time we consider interference to be a problem, okay? In that, you know, if something interferes with your cell phone signal or your Wi-Fi, it doesn't work, okay? And that's sort of true. Okay, interference most of the time is a bit of a problem. Okay, but we do actually use interference in a few conditions to help us amplify things, okay, make them louder, or destroy sound, okay, in order to like diminish the volume of something. All right, so two kind of prime places where that would happen would be in most musical instruments. Most musical instruments channel waves in such a way that they overlap in the same places, causing them to naturally or acoustically amplify themselves, not requiring any power. All right, so the resonant cavity of any string instrument, okay, a guitar, a bass, okay, or whatever, okay, all of those, okay, have a big resonating cavity that has a certain shape. Kind of all guitars and string instruments have that kind of hourglass shape, okay, that channels the waves around inside and allows them to interfere with each other in such a way that the sound gets louder. Okay, we call that resonance. A muffler on a car does the exact opposite. A muffler on a car sends sound waves bouncing around inside in such a way that they interfere destructively with each other, causing their volume to be diminished, hence muffling the sound of the engine. All right, unless, you know, you're redneck Joe who drives around with straight pipes coming straight out the headers, okay, and, you know, signals the coming of the apocalypse whenever they drive past your house. All right, yeah, so if you have the redneck mobile, go out and get some freaking mufflers because you're just annoying everybody and no one thinks you're cool. Yeah. Okay. Sorry about that. Okay. All right. So what we got to do today is understand what happens when two waves occupy the same space. Okay. We got to learn the two types of interference, and we've talked about those already: destructive, constructive. Okay. Those are the two types of interference. Either the waves are getting bigger or the waves are getting smaller. There's only one way or the other. Okay, and understand how that can be applied to practical uses. All right, so there's a very straightforward way to deal with situations in which two or more waves pass through the same place simultaneously. So if I've got these situations here, and I'm going to do these with the real Slinky here in a minute, okay, I'll have these two waves, which I kind of described before, okay, that are moving towards each other. All right, they're both up. We call these actually just pulses because a wave actually has to have an up and a down. So these are two pulses that are approaching each other. When they merge, that is, they occupy the same space at the same time, the medium has to absorb essentially all the energy of both pulses, meaning its amplitude has to reflect the sum of them. So if each one of these was +1, when they're overlapping, the amplitude will be +2. It's really easy. Okay, we make it sound really hard by giving it a very complex name. Okay, the principle of linear superposition. Add the amplitudes. Okay, it's really easy. Okay, if I have a pulse that is up and a pulse that's down, like I have in this situation here, when they completely overlap, there will be no displacement at all. Okay, because their energies will cancel each other out. All right, then the key thing here, guys, is that afterwards, the original pulses reappear. Interference does not destroy a wave permanently. Okay, if we can get it to, keep going and keep interfering, eventually our end product is a silenced or, or a low amplitude kind of thing that comes out of a muffler. But, okay, in a situation like this, there's only interference when the waves are actually overlapping. Okay, once they're not overlapping anymore, they go right on their way happily. Everyone kind of follow me on that one, okay? Because we get this idea that interference is somehow permanent, okay? But if you've ever noticed, when you're getting interference on your phone or something like that, all you have to do is take a couple steps one way or the other and suddenly it clears up, right? It's just because the interference was only happening in that spot. As soon as you move away from that spot, the interference disappears, okay? The waves were just overlapping in a destructive way in that particular spot. Okay, making sense? All right. So, show you what this looks like here with the real slinkies. All right, so we get those waves, they come through, they pass through each other, there's an instant of interference, and then that instant is over. Okay, they occupy the same space at the same time for that. All right, so in the diagram here, okay, we've got pulses that are up and one that's, the other is down, okay, and that gives us the two different kinds of interference. So if I've got pulses that are going to cancel each other entirely or partially, that's destructive interference. Okay, if I've got pulses that are going to amplify each other, that is, they have amplitudes that are both positive or both negative, then that's constructive interference because it's building the amplitude, right, rather than taking it apart. Everybody with me there? Right, so those are the two kinds of interference. Constructive interference, where the amplitude increases. Destructive interference, where the amplitude diminishes. Okay, does it have to be total to qualify? Like, does it have to make does destructive interference have to completely destroy the amplitude? No, it can be partial. All right, if I have like a +3 wave and a -1 wave hitting each other, that's still destructive interference because the amplitude is going to be less. Okay, it's going to be +2 after that. All right, so that's what we got to look at there. So that's the principle of linear superposition in a nutshell. Okay, it's not terribly difficult. All right, so if I have two opposite pulses, then like we say, we get that destructive interference. The slinky appears straight. Okay, the adding together of those individual pulses is the principle of linear superposition. All right, so basically every semester on this unit exam, one of the questions is, here are two waves. Draw what they would look like when they overlap. All right, so if I give you a picture that looks like okay, so maybe I give you one wave that looks like this, right? And I say that its amplitude is +2 and -2, right? And then I show you another wave that looks like this one. Right? And I say, draw the resulting shape of the medium or draw the resulting wave. What's that resulting wave going to look like? Yeah, it's going to be +3 on one side. It's going to be -3 on the other. Okay, it's a pretty easy question. Like, there's really no reason for anyone to not get it entirely right. Okay, that would be our resulting wave. Now, I would probably have like a grid there so that you could make sure you had the exact correct amplitudes for both. Okay, it's a relatively easy question, just checks whether you understand the principle of linear superposition. Okay, now, very rarely do you have just like, oh, here's one wave and here's another wave and what happens when they pass through each other. Most of the time, waves are traveling in what we call a train. Okay, there's many waves that are following each other because there's some source that keeps producing them, right? So if that's the case, okay, I've got wave A here and I've got wave B here. I have to decide whether this is going to be constructive or destructive interference by determining whether or not they are in phase. Okay, what I mean by in phase is, do they line up with each other, all right? So wave A and wave B are in phase because when one is up, so is the other. When one is down, so is the other. They are exactly in phase. They have the same wavelength, the same orientation, same frequency. Okay, all of that stuff is the same. So they are in phase. So this will be an example of what kind of interference? Constructive interference. All right, so my resulting waveform would look like this. Okay, there would be an increased amplitude. In the case of this one here, okay, I have wave A, so same as before, but now I have wave C, right? These ones are out of phase, right? They have the same wavelength, they have the same frequency, but they're out of phase. When one is up, the other is down. And so this is going to be an example of destructive interference, okay? And as a result, I'll have a diminished or decreased amplitude as my resulting wave. Okay. All right, it's really easy to see when you're dealing with what we call one-dimensional waves. Right? A slinky on the floor is a one-dimensional wave. It can only be up or down, right? And that's it. But when we start dealing with two-dimensional waves, like sound waves traveling through a room, okay, the same principles apply, but you can't visualize them because the medium is air and sound waves are invisible. Okay, so we have to be able to determine, okay, where is constructive interference occurring, where is destructive interference occurring with the sound waves. How do we determine that? If I have a room and it just has two speakers in it, if I walk around the room, what am I going to notice? Yeah, it's quieter in some places and louder in others, right? The same thing is going to happen, but in a three-dimensional, or well, we'll say two-dimensional space, okay, where I can find areas where they're overlapping constructively, areas where they're overlapping destructively, okay? So there'll be areas of loud and quiet sound, right? Now, in the practical sense, it doesn't work perfectly that way because the sound also reflects off the walls, okay, and causes those kind of dead spots to disappear. But if you had these walls coated, okay, in like an anechoic kind of foam, right, then you would actually find quiet spots and loud spots throughout the room because there would be no secondary waves. They'd all be absorbed by the walls, okay? And it's really strange. Okay, an anechoic chamber, if you've ever been in one, is really like, it looks like you're inside a meat grinder. Okay? It looks really weird. There's all these jagged edges and stuff because that helps to keep the sounds from reflecting uniformly. It's really weird looking. Okay, all right. So here's what we've got. I've got this receiver that's connected to two speakers, and all it's doing is producing a tone. All right, so a constant sound of known frequency. Right. We'll say that the wavelength of the sound it's producing is 1 meter, just for simplicity's sake. Right. So if I'm standing right here and I'm equidistant from both speakers, then the waves from this speaker and the waves from the other speaker travel the same number of wavelengths before they get to me, which means they're going to arrive in or out of phase. In phase, right? Because they're exactly the same wave. They've traveled exactly the same number of wavelengths, so they'll arrive crest to crest, trough to trough, and I will hear a loud sound. Everyone okay with that idea? All right. What happens if I back this speaker up half a meter? Then they'll be out of phase, right? Because we said the wavelength is a half a meter long. So if I move this, or sorry, it was 1 meter long. If I move this back half a meter, I've moved it back half a wavelength. Now, the waves traveling from it will travel 3.5 wavelengths. This one will travel 3, and they'll meet crest to trough, and I will hear nothing at this position. Okay, so if I was looking at it from above and I could actually visualize the sound waves, this is what I would see. Okay, the light blue are the ones from speaker A, and the dark blue are the ones from speaker B. So if I was standing right here, I would hear loud or quiet? Loud, okay? Because that's two crests overlapping, okay? Two crests are overlapping right there, so I would hear a very loud sound. All right, what if I'm standing here? Okay, maybe it's easier to visualize if I do this. I'm going to make dotted lines for the troughs, okay? So I'm going to use green dotted lines for speaker A. Right, because the solid lines represent crests, okay, and these other lines here represent troughs, okay, and I'll do the same thing. I'll use dark blue here for the ones from speaker B. Okay, so if I'm standing right here on this X, okay, I'm standing on a crest from one speaker and a trough from the other. What do I hear? Nothing. Okay, that's an area of complete destructive interference. What if I'm standing right here? Loud. I'm standing on a trough from one and a trough from the other. Okay, they're in phase at that point, so I would hear a loud sound. Okay, anywhere where I'm at the same point in the wave, I hear something loud. If I'm standing anywhere where I'm at the opposite point in a wave, okay, like a crest and a trough, then I'll hear nothing because they'll completely cancel each other out. Right? So the application here is this. If you're building like a home theater system or something like that, you want to put the seating locations where constructive interference is likely to occur for most wavelengths. You obviously can't have it for all wavelengths because it's different, okay? But for most wavelengths, you want to have the seating positions in spots where they're going to interfere constructively, right? And what can even be done with really modern receivers and home theater equipment is they can delay certain frequencies from one speaker, okay? And then actually make it so that they interfere constructively at the same spot regardless of their frequency, with just a slight hesitation between when they're emitted. Okay, it doesn't affect your viewing experience or listening experience. Okay, but it makes, like, you don't notice it, but it makes it louder. Okay, without having to use as much power. Right? Everyone okay with that? Because if this is just producing a single tone, it doesn't matter how much I crank it up. If I'm standing in a spot where a crest meets a trough, it's going to be silent in that spot. Okay? It's odd, but it would be true. And all you would have to do is like take a slight step to the side and all of a sudden the volume would reappear. Okay? Go back in, you'd have the silent spot, like the cone of silence. Okay? And then you'd come over here and you could be standing in a spot where it's like unbearably loud. Okay? It's really strange. We see light do exactly the same thing. Okay? It's just light has such a small wavelength that you can't see it. You can't see the pattern. But if you put a screen far enough away, you get stripes on it representing areas of constructive and destructive interference. It was actually the experiment that proved light was a wave, used this pattern to prove it. Okay, so these ones are exactly in phase, okay? And we said if I backed one of these speakers up half a wavelength, then I would be standing at a position where there would be destructive interference. So what determines whether you have constructive or destructive interference is the difference in wavelengths from each source. All right, so if I'm standing right here, okay, then waves from speaker B have traveled, okay, they've traveled 1, 2, 3.5 wavelengths. Okay, so they traveled 3.5 from speaker B, and from speaker A, they've traveled 1, 2, 3, 4.5. So 4.5 minus 3.5 is what? 1. 1.0. So they are arriving in phase. Okay, they've traveled one wavelength, full wavelength, one full cycle different, but they're arriving in phase. Okay, if I'm standing at, let's say, this point right here, okay, then waves from speaker A have traveled 1, 2, 3, 4 wavelengths. Okay, but the ones from speaker B have traveled 1, 2.5. Okay, well, the difference in travel is 1.5 wavelengths, so now I hear a quiet sound. Right? That's what determines whether it's loud or quiet, is the difference in the number of wavelengths traveled from each source. So all you have to do is figure out how many wavelengths from each source, subtract them, and you know right away. Is it a decimal, like is it 0.5, or is it a whole number? If it's a whole number, constructive. If it's 0.5, they're out of phase completely. All right. Okay, so in general, okay, that's what we want to do. We want to find, okay, the important issue is the difference in the distances traveled by each wave in terms of their wavelength, the number of wavelengths different. Okay, if it's a whole number, then it's constructive. Okay, if it's a half, then it's destructive. All right, copy this question down here. Right, we're going to do it together because it is exactly like the one that I will put on your unit exam to do with interference. All right, so I'll give you a minute to get a copy down, diagram included. All right, so if we're approaching a question like this, the first thing we have to remember is that what determines whether I hear a loud sound or a quiet sound is how many wavelengths of travel it is from each speaker. So if I'm going to know how many wavelengths it is from each speaker, probably the first thing I should calculate about this sound is its wavelength. All right, so I'm going to use the formula we learned yesterday, okay, the universal wave equation. Can you guys even see that? Maybe red is better. Okay, so for that one we have V equals F times lambda. I'm trying to find lambda, so that's going to be V over F. They told me V is 343 meters per second. They told me F is 214 hertz. All right, so I'm going to take my 343 and divide it by 214, and that should be 1.6? Yeah, okay, 1.6 meters. All right, so now I have my wavelength. So if I'm going to figure out now how many wavelengths there are from each speaker, I need to know how far I'm standing from each speaker. All right, I already know I'm 2.4 meters from the first one, but I don't know how far I am from this one. Can I figure it out? Yeah, I just used Pythagoras. All right, so we'll have a quick Pythagoras calculation here. All right, I think it comes out to 4 meters, is it not? 4.0? Yeah. Okay, so I just go 2.4 squared plus 3.2 squared, square rooted. This side is 4 meters long. Okay, now that I know those lengths, now I need to figure out how many waves are in that length. All right, since I know the one wave is 1.6 meters, that's not too tough. All right, so I'm going to go 2.4 meters divided by 1.6, okay, and that'll give me 1.5, right? Right, so there's 1.5 wavelengths between this speaker and the observer. Right, then I've got to do the same thing here, 4 divided by 1.6, and that should give me the 2.5. Yeah, okay, so there's 2.5 wavelengths between this speaker and the observer. All right, so does this person hear a loud sound or a quiet sound? Loud. Okay, they hear a loud sound because the difference in travel is 1 wavelength. Okay, this is arriving trough to trough, but it's still in phase because it's 1 full wavelength difference. Does that make sense? Okay, so this person would hear a loud sound at this location. Right, guys, there has never been a unit exam where I did not have a 2-speaker question. Right, so expect you'll see something like this. Right, all you have to do a universal wave equation calculation, a Pythagorean theorem calculation, calculate the number of wavelengths, and subtract them. All right, now it's a 5-mark question, but if all you write, because you can't remember how to do it, is loud, and you actually guess right, you're going to get 1 mark for guessing right. And I'm going to write in big capital letters, proof, beside it. Okay, you can get a mark for being a good guesser, but you got to prove to me that you figured it out, not that you knew it was a 50-50 chance of getting it right and just wrote something down. Okay. All right, any questions on how that one worked? Everybody's good with that one? Okay. Let me give you a little bit of time with the slinkies. Okay, so we can, okay, just getting in a group or whatever, you can take a slinky, okay, put it on the floor, okay, do some stuff with waves, see what happens with them, all right, see how that goes.